The color temperature of a light source is the temperature of an ideal black-body radiator that radiates light of comparable hue to that of the light source. Color temperature is a characteristic of visible light that has important applications in lighting, photography, videography, publishing, manufacturing, astrophysics, horticulture, and other fields. In practice, color temperature is only meaningful for light sources that do in fact correspond somewhat closely to the radiation of some black body, that is those on a line from reddish-orange via yellow and more or less white to bluish-white. It does not make sense to speak of the color temperature of, for example, a green or a purple light. Color temperature is conventionally stated in the unit of absolute temperature, the Kelvin, having the unit symbol K. Color temperatures over 5000 kelvins are called cool colors, while lower color temperatures are called warm colors. This relation, however, is a psychological one in contrast to the physical relation implied by Wien's displacement law, according to which the spectral peak is shifted towards shorter wavelengths for higher temperatures. Categorizing different lighting. The color temperature of the electromagnetic radiation emitted from an ideal black body is defined as its surface temperature in kelvins, or alternatively in myads. This permits the definition of a standard by which light sources are compared. To the extent that a hot surface emits thermal radiation but is not an ideal black body radiator, the color temperature of the light is not the actual temperature of the surface. An incandescent lamp's light is thermal radiation, and the bulb approximates an ideal black body radiator, so its color temperature is essentially the temperature of the filament. Many other light sources, such as fluorescent lamps, or LEDs, emit light primarily by processes other than thermal radiation. This means that the emitted radiation does not follow the form of a black body spectrum. These sources are assigned what is known as a correlated color temperature. CCT is the color temperature of a black body radiator which to human color perception most closely matches the light from the lamp. Because such an approximation is not required for incandescent light, the CCT for an incandescent light is simply its unadjusted temperature, derived from the comparison to a black body radiator. The sun closely approximates a black body radiator. The effective temperature, defined by the total radiative power per square unit, is about 5780 K. The color temperature of sunlight above the atmosphere is about 5900 K. As the sun crosses the sky, it may appear to be red, orange, yellow or white depending on its position. The changing color of the sun over the course of the day is mainly a result of scattering of light and is not due to changes in black body radiation. The blue color of the sky is caused by Rayleigh scattering of the sunlight from the atmosphere, which tends to scatter blue light more than red light. Daylight has a spectrum similar to that of a black body with a correlated color temperature of 6500 K or 5500 K. For colors based on black body theory, blue occurs at higher temperatures, while red occurs at lower, cooler, temperatures. This is the opposite of the cultural associations attributed to colors, in which red is hot, and blue is cold. Color temperature applications, lighting. For lighting building interiors, it is often important to take into account the color temperature of illumination. For example, a warmer light is often used in public areas to promote relaxation, while a cooler light is used to enhance concentration in offices. CCT dimming for LED technology is regarded as a difficult task, since binning, age and temperature drift effects of LEDs change the actual color value output. Here feedback loop systems are used, for example with color sensors, to actively monitor and control the color output of multiple color mixing LEDs. Aquaculture. In fish keeping, color temperature has different functions and foci, for different branches. In freshwater aquaria, color temperature is generally of concern only for producing a more attractive display. Lights tend to be designed to produce an attractive spectrum, sometimes with secondary attention to keeping plants alive. In a saltwater reef aquarium, color temperature is an essential part of tank health. Within about 400 to 3000 nanometers, light of shorter wavelength can penetrate deeper into water than longer wavelengths, providing essential energy sources to the algae hosted in coral. This is equivalent to an increase of color temperature with water depth in this spectral range. Because coral, typically living in shallow water, receives intense, direct tropical sunlight, the focus was once on simulating this with 6500 K lights. Higher temperature light sources have become more popular, first with 10,000 K and more recently 16,000 K and 20,000 K. Meanwhile, actinic lighting is used to make the somewhat fluorescent colors of many corals and fish pop, creating brighter display tanks. Digital photography. In digital photography, color temperature is sometimes used interchangeably with white balance, which allow a remapping of color values to simulate variations in ambient color temperature. Most digital cameras and raw image software provide presets simulating specific ambient values, while others allow explicit entry of white balance values in kelvins. These settings vary color values along the blue-yellow axis, while some software includes additional controls adding the magenta-green axis, and are to some extent arbitrary and subject to artistic interpretation. Photographic film. Photographic emulsion film sometimes appears to exaggerate the color of the light, as it does not adapt to lighting color as human visual perception does. An object that appears to the eye to be white may turn out to look very blue or orange in a photograph. The color balance may need to be corrected while shooting or while printing to achieve a neutral color print. Photographic film is made for specific light sources, and used properly, will create a neutral color print. Matching the sensitivity of the film to the color temperature of the light source is one way to balance color. If tungsten film is used indoors with incandescent lamps, the yellowish-orange light of the tungsten incandescent lamps will appear as white in the photograph. Filters on a camera lens, or color gels over the light source, may also be used to correct color balance. When shooting with a bluish light source such as on an overcast day, in the shade, in window light, or if using tungsten film with white or blue light, a yellowish-orange filter will correct this. For shooting with daylight film under warmer light sources such as sunsets, candlelight or tungsten lighting, a bluish filter may be used. If there is more than one light source with varied color temperatures, one way to balance the color is to use daylight film and place color-correcting gel filters over each light source. Photographers sometimes use color temperature meters. Color temperature meters are usually designed to read only 2 regions along the visible spectrum. More expensive ones read 3 regions. However, they are ineffective with sources such as fluorescent or discharge lamps, whose light varies in color and may be harder to correct for. Because it is often greenish, a magenta filter may correct it. More sophisticated colorimetry tools can be used where such meters are lacking. Desktop publishing. In the desktop publishing industry, it is important to know or monitor a unregistered trademark's color temperature. Color matching software, such as Apple's ColorSync for Mac OS, will measure a monitor's color temperature and then adjust its settings accordingly. This enables on-screen color to more closely match printed color. Common monitor color temperatures, along with matching standard illuminance in parentheses, are as follows: 5000 K, 5500 K, 6500 K, 7500 K, 9300 K. D50 is scientific shorthand for a standard illuminant, the daylight spectrum at a correlated color temperature of 5000 K. Similar definitions exist for D55, D65 and D75. Designations such as D50 are used to help classify color temperatures of light tables and viewing booths. When viewing a color slide at a light table, it is important that the light be balanced properly so that the colors are not shifted towards the red or blue. Digital cameras, web graphics, DVDs, etc., are normally designed for a 6500 K color temperature. The sRGB standard commonly used for images on the Internet stipulates a 6500 K display white point. TV, video, and digital still cameras. The NTSC and PAL-TV norms call for a compliant TV screen to display an electrically black and white signal at a color temperature of 6500 K. On many consumer-grade televisions, there is a very noticeable deviation from this requirement. However, Higher-end consumer-grade televisions can have their color temperatures adjusted to 6500 K by using a pre-programmed setting or a custom calibration. Current versions of ATSC explicitly call for the color temperature data to be included in the data stream, but old versions of ATSC allowed this data to be omitted. In this case, current versions of ATSC cite default colorimetry standards depending on the format. Both of the cited standards specify a 6500 K color temperature. Most video and digital still cameras can adjust for color temperature by zooming into a white or neutral colored object and setting the manual white balance. The camera then shows true white is white and adjusts all the other colors accordingly. White balancing is necessary especially when indoors under fluorescent lighting and when moving the camera from one lighting situation to another. Most cameras also have an automatic white balance function that attempts to determine the color of the light and correct accordingly. While these settings were once unreliable, they are much improved in today's digital cameras, and will produce an accurate white balance in a wide variety of lighting situations. Artistic application via control of color temperature. Video camera operators can white balance objects which aren't white, downplaying the color of the object used for white balancing. For instance, they can bring more warmth into a picture by white balancing off something light blue, such as faded blue denim. In this way white balancing can serve in place of a filter or lighting gel when those are not available. Cinematographers do not white balance in the same way as video camera operators. They can use techniques such as filters, choice of film stock, pre-flashing, and after shooting, color grading. Cinematographers also work closely with set designers and lighting crews to achieve the desired effects. For artists, most pigments and papers have a cool or warm cast, as the human eye can detect even a minute amount of saturation. Gray mixed with yellow, orange or red is a warm gray. Green, blue, or purple, create cool grays. Note that this sense of temperature is the reverse of that of real temperature. Blue is described as cooler even though it corresponds to a higher temperature black body. Lighting designers sometimes select filters by color temperature, commonly to match light that is theoretically white. Since fixtures using discharge-type lamps produce a light of considerably higher color temperature than tungsten lamps, using the two in conjunction could potentially produce a stark contrast, so sometimes fixtures with HID lamps, commonly producing light of 6000 to 7000 K, are fitted with 3200 K filters to emulate tungsten light. Fixtures with color mixing features or with multiple colors, are also capable of producing tungsten-like light. Color temperature may also be a factor when selecting lamps, since each is likely to have a different color temperature. Correlated color temperature. The correlated color temperature is the temperature of the Planckian radiator whose perceived color most closely resembles that of a given stimulus at the same brightness and under specified viewing conditions. Motivation: black body radiators are the reference by which the whiteness of light sources is judged. A black body can be described by its color temperature, whose hues are depicted above. By analogy, nearly Planckian light sources such as certain fluorescent or high-intensity discharge lamps can be judged by their correlated color temperature. The color temperature of the Planckian radiator that best approximates them. The question is, what is the relationship between the light source's relative spectral power distribution and its correlated color temperature? Background. The notion of using Planckian radiators as a yardstick against which to judge other light sources is not a new one. In 1923, writing about grading of illuminants with reference to quality of color the temperature of the source as an index of the quality of color, Priest essentially described CCT as we understand it today, going so far as to use the term apparent color temperature, and astutely recognized three cases, those for which the spectral distribution of energy is identical with that given by the Planckian formula. Those for which the spectral distribution of energy is not identical with that given by the Planckian formula, but still is of such a form that the quality of the color evoked is the same as would be evoked by the energy from a Planckian radiator at the given color temperature. Those for which the spectral distribution of energy is such that the color can be matched only approximately by a stimulus of the Planckian form of spectral distribution. Several important developments occurred in 1931. In chronological order, Raymond Davis published a paper on correlated color temperature. Referring to the Planckian locus on the UG diagram, he defined the CCT as the average of the primary component temperatures, using trilinear coordinates. The CIE announced the XYZ color space. Dean B. Judd published a paper on the nature of least perceptible differences with respect to chromatic stimuli. By empirical means he determined that the difference in sensation, which he termed IE for a discriminatory step between color euro and pindum, was proportional to the distance of the colors on the chromaticity diagram. Referring to the chromaticity diagram depicted aside, he hypothesized that Ki E equals C1A C2 equals max, A1A A2, G1A G2. These developments paved the way for the development of new chromaticity spaces that are more suited to the estimation of correlated color temperatures and chromaticity differences. Bridging the concepts of color difference and color temperature, Priest made the observation that the eye is sensitive to constant differences in reciprocal temperature. A difference of 1 micro-reciprocal degree is fairly representative of the doubtfully perceptible difference under the most favorable conditions of observation. Priest proposed to use the scale of temperature as a scale for arranging the chromaticities of the several illuminants in a serial order. Over the next few years, Judd published 3 more significant papers. The first verified the findings of Priest, Davis, and Judd, with a paper on sensitivity to change in color temperature. The second proposed a new chromaticity space, guided by a principle that has become the holy grail of color spaces, perceptual uniformity. By means of a projective transformation, Judd found a more uniform chromaticity space in which to find the CCT. Judd determined the nearest color temperature by simply finding the nearest points on the Planckian locus to the chromaticity of the stimulus on Maxwell's color triangle, depicted aside. The transformation matrix he used to convert X, Y, Z tri-stimulus values to R, G, B coordinates was. From this, one can find these chromaticities. The third depicted the locus of the isothermal chromaticities on the CIE 1931 X, Y chromaticity diagram. Since the isothermal points formed normals on his UCS diagram, transformation back into the XY plane revealed them still to be lines, but no longer perpendicular to the locus. Calculation. Judd's idea of determining the nearest point to the Planckian locus on a uniform chromaticity space is current. In 1937, McAdam suggested a modified uniform chromaticity scale diagram, based on certain simplifying geometrical considerations. This chromaticity space became the CIE 1960 color space, which is still used to calculate the CCT. Using other chromaticity spaces, such as UV, leads to non-standard results that may nevertheless be perceptually meaningful. The distance from the locus is traditionally indicated in units of positive for points above the locus. This concept of distance has evolved to become delta E, which continues to be used today. Robertson's method. Before the advent of powerful personal computers, it was common to estimate the correlated color temperature by way of interpolation from lookup tables and charts. The most famous such method is Robertson's, who took advantage of the relatively even spacing of the Myers scale to calculate the CCTTC using linear interpolation of the isotherms' Myers values. Whereunder the color temperatures of the lookup isotherms and I is chosen such that, if the isotherms are tight enough, one can assume, leading to the distance of the test point to the ITH isotherm is given by. Where is the chromaticity coordinate of the ITH isotherm on the Planckian locus and μ is the isotherm's slope? Since it is perpendicular to the locus, it follows that where L is the slope of the locus at. Precautions. Although the CCT can be calculated for any chromaticity coordinate, the result is meaningful only if the light sources are nearly white. The CIE recommends that the concept of correlated color temperature should not be used if the chromaticity of the test source differs more than from the Planckian radiator. Beyond a certain value of, a chromaticity coordinate may be equidistant to 2 points on the locus, causing ambiguity in the CCT. Approximation. If a narrow range of color temperatures is considered those encapsulating daylight being the most practical one can approximate the Planckian locus in order to calculate the CCT in terms of chromaticity coordinates. Following Kelly's observation that the isotherms intersect in the purple region near Makehami proposed this cubic approximation, CCT, x, y, equals a 449N3 plus 3525N2 is 6823.3 N plus 5520.33, where N equals /YAE, is the inverse slope line, and is the epicenter. Quite close to the intersection point mentioned by Kelly. The maximum absolute error for color temperatures ranging from 2856 Ok to 6504 Ok is under 2 Ok. A more recent proposal, using exponential terms, considerably extends the applicable range by adding a second epicenter for high color temperatures, CCT, x, y, equals AO plus A1 EXP, ANT1, plus A2 EXP, ANT2, plus A3 EXP, ANT3, where N is as before and the other constants are defined below. The inverse calculation, from color temperature to corresponding chromaticity coordinates, is discussed in Planckian locus. Color rendering index. The CIE color rendering index is a method to determine how well a light source's illumination of 8 sample patches compares to the illumination provided by a reference source. Cited together, the CRI and CCT give a numerical estimate of what reference light source best approximates a particular artificial light, and what the difference is. Spectral power distribution. Light sources and illuminants may be characterized by their spectral power distribution. The relative SPD curves provided by many manufacturers may have been produced using 10 nm increments or more on their spectroradiometer. The result is what would seem to be a smoother power distribution than the lamp actually has. Owing to their spiky distribution, much finer increments are advisable for taking measurements of fluorescent lights, and this requires more expensive equipment. Color temperature in astronomy. In astronomy, the color temperature is defined by the local slope of the SPD at a given wavelength, or, in practice, a wavelength range. Given, for example, the color magnitudes B and V which are calibrated to be equal for an AOV star, the stellar color temperature is given by the temperature for which the color index of a blackbody radiator fits the stellar one. Besides other color indices can used as well. The color temperature may differ largely from the effective temperature given by the radiative flux of the stellar surface. For example, the color temperature of an AOV star is about 15,000 kelvins compared to an effective temperature of about 9,500 kelvins. See also, Kruithof curve, luminous efficacy, over illumination, brightness temperature, effective temperature, whiteness, Cullum tamarism, references. Further reading, Stbell, Leslie. John Compton. Ira Current. Richard Zakiya. Basic Photographic Materials and Processes. Boston, Focal Press. ISBN A0-240-80405-8. Iseki, Gar 1/4 NTER. Stiles, Walter Stanley. 3.11 Distribution temperature, color temperature, and correlated color temperature. Color Science, Concept and Methods, Quantitative Data and Formula. New York, Wiley PPA 224 €229. ISBN A0-471-02106-7. External links, Kelvin to RGB calculator from academo.org, Boyd, Andrew. Kelvin temperature in photography at the Discerning Photographer. Charity, Mitchell. Body/what color is a black body? sRGB values corresponding to black bodies of varying temperature. Lindblom, Bruce. ANSIC implementation of Robertson's method to calculate the correlated color temperature of a color in XYZ. Konica Minolta Sensing. The Language of Light.